Hello and welcome to New Planet School. Today we are going to ask the question, what is calculus? We're not going to go into too many details about what calculus is, but really just talk about the big picture of what it is and what it's useful for. So before getting started on what calculus is, let's just step back and think about where calculus lives in the world of math. And the reason that's important is that math, as I say here, is a house that needs to be built. You build a foundation and it builds up from the bottom, and finally you have a house that you've built. And typically you'll start with, for example, algebra, maybe trigonometry, geometry, and calculus, and they each build on each other. As Rene Descartes says here, each problem that I solve becomes a rule which serve afterwards to solve other problems. And it's important to keep this in mind as you learn calculus, because as you do calculus, you're going to be using geometry, you're going to be using trigonometry, you're going to be using algebra. When I used to do a lot of tutoring of calculus, I noticed that not very often did people actually make calculus mistakes. What would happen is they would make geometry mistakes, trigonometry mistakes, and algebra mistakes trying to solve a calculus problem. So be clear in your mind what you're doing when you try to solve a calculus problem, because the problem you may be having may not actually be calculus. It may be that the calculus is confusing you and you're not able to do algebra anymore. So keep that in mind. So let's start off by talking about some simple things that we know to motivate why calculus is actually needed. So here I have a line, and let's ask ourselves, what do we know about this line? Well, one of the things we know is what its slope is. And remember, the slope, which is usually m, is rise over run. And in this case, the rise is 3. And you can see here that the run is 5. So the slope of this line is 3/5. And in fact, you can see that the intercept here is 1. So we can write this equation of this line as y equals 3/5 x plus 1. And you see here we're using concepts from algebra. And what it tells us is that this line has a constant slope of 3/5. Pretty simple. What else could we possibly want to know? Suppose we want to know the length of this line. Well, that's pretty simple, because if we label this over here, say h, because it's the hypotenuse of this triangle, and it is a right triangle, then we can use the fact that the hypotenuse is equal to the square root of the sum of the squares of the sides from the Pythagorean theorem. So we can get the length very easily of this using something we know from trigonometry. So we've used algebra and we've used trigonometry, and everything so far has been fairly easy. Now let's think about the area. This is not something you probably have thought of as much, but imagine, for example, that this was, say, my income over time, and I wanted to know what my total income is. So I want to know this area under this curve, or this line. How would I do that? In fact, it's very easy to do that, because I can break it up into a rectangle here, and the area of a rectangle is the base times the height, and then I can add to that the area of this triangle, which is 1/2 base times the height. So the first one is the base, which is 5, times the height, which is 1, and then I add to that 1/2 the base, which is 5, and the height, which is 3. And I can very easily get the area under this line. It's a pretty simple thing, and here I'm using essentially, say, geometry. So I've used a little algebra, a little trigonometry, and a little geometry, and I've been able to solve these 3 problems for a line. No problem. Now, let's think about curves. Let's try to do the same thing. How do I get the slope of this curve? Well, it actually doesn't make any sense, because lines have slopes. Do curves have slopes? That's a good question. Now, what you can see is we can kind of get an estimate by saying, well, there's like a local slope. Let's call that a local slope here, which is 0, and clearly there's a slope up here, loosely speaking, and another slope here, and these things we'll call tangent lines, which, since lines have a slope, we can define a line that at some point sort of has the same slope. But in general, it's not a very well-defined concept. Okay, what about the length of the line? Well, that's even harder. I don't know of any way to figure out what the length of this line is, because we pretty much only know how to find the length of lines when they're part of a triangle. And you could see that you would get, if this were a right triangle, so I could draw it better, I would get close to the right length of the line, but not quite the right length. Again, we have a problem. Okay, what about the area? So suppose I wanted to know, again, this is, say, my income over time. This is looking a little bit better. It's going up very fast. And I want to know the area under here. How would I do that? Well, again, I could break this piece up into a rectangle, but clearly getting the area of a shape that like this is not very easy. So you can see how concepts that are very familiar to us, as soon as we have a curve, that is, we have something that's changing, things become a little bit more difficult. And this is where calculus comes in. Now, does that matter? Let's look. This is definitely a problem. Look around you right now. Look at the keyboard in front of you. Look to your left. Look to your right. Everything around you is composed of curves. So if we had to rely only on trigonometry and geometry and algebra, we could almost do nothing in the real world, whether it's medicine, architecture, engineering, entertainment, finance. We couldn't understand or do anything with these concepts without being able to handle change and the fact that things typically are curving. That's what I mean by change here. Whether it's energy generation, climate, car design, geography, everything is composed of things with very unusual shapes. So, what are we going to do? We're going to use calculus. And this is the reason that calculus was invented a long time ago, was to handle change, and it introduces into math the concept of limits. So if you've only done algebra and geometry and so forth, you probably have not learned about the concept of a limit. It's really interesting, and it's what calculus is. So if you understand everything about limits that I'm going to talk about on this one slide, you'll understand what calculus is and why it's needed. So let's start off with the concept of a sequence, which is an easy way to introduce the concept of a limit. The word limit, of course, in English has many meanings, and here it has a very specific meaning that can be introduced with the concept of a sequence. So suppose we have this sequence of numbers. It starts off with 1, 2/3, 3/5, and so forth. And I ask the question, what is the final value? So these 3 dots mean I keep on going and going and going. And then I ask, what is the final value here? In other words, what is the limiting value, or just the limit? That's what I want to know. Now, if you look at the sequence of numbers, you can see something obvious. They look like they're getting smaller, so maybe it's going to 0. Maybe it becomes negative. It's not clear yet. An easy way to figure it out is to take these numbers and make a graph of them, which I've done here. Here's the first one, which is 1. And you can see the next number indeed is smaller. It's about 2/3 right there. The next number is smaller, but not that much smaller. 3/5 is 0.6. And then the next one is smaller again, but not as small. It's not dropping as much. So what you can see is it's always dropping, but not by as much every time. And what happens is if you keep running this sequence out, it eventually approaches a limiting value of 0.5. So we can write in here that the limiting value, or the limit, is 1/2. So how could we do that mathematically if we didn't happen to have the graph? It turns out the way I made this sequence is I used this. This is how I did it. And this is n equals 0, n equals 1, n equals 2, and this would be n equals infinity. So the way we write this in math is we don't want to write the word limit out every time, so we shorten it to just lim, which means limit, and we write this as the limit as n goes to infinity. So we get to use this very fancy math notation, and that tells us we're going to take this n to be very large. Well, how do I use this fancy notation? Well, one thing we can do is we can notice that when n is really, really large, adding 1 to it doesn't do a whole lot. So we'll just write that as n. The other thing, we can look at the denominator, same thing. 2n, which is even bigger, means that we can neglect this 1 also. So we'll just write that as 2n, and we'll neglect the plus 1. Now we can cancel the n's. We really should write the limit in here again. And you can see the numerator is 1, the denominator is 2, and sure enough, we get the limiting value of 1/2. So you can see how to get there. Now, this is probably fairly abstract, and you're probably thinking, I'll never do this. How does this connect to something I actually want to know about in math? So let's go to the next step and look at a function. And I chose a specific function here to look at, which is sine x over x. So let's look at this, and let's ask the question. We can ask many questions. Let's say we ask the question, what is the limit as x goes to 0, which just means we're going to get to smaller and smaller and smaller and smaller x of sine x over x. What is that? Well, we can write that sine x, if you remember from trigonometry, is sine of 0 is 0. And the limit as x goes to 0 of x is 0. Well, this is a problem. This is an indeterminate form. If I have 0 over anything, I get 0. On the other hand, anything over 0 is infinity. So this is either 0 or infinity, but it can't be both. So this makes absolutely no sense. So we have to use the concept of a limit very carefully. And let me just show you how we can do that. Imagine we could make a graph of this function that looks like this, and what we do is we sneak up on 0. So what we do is we start here, we evaluate sine x over x, we do it again, we do it again, we do it again, we do it again. So far there's no problem. We keep doing it, we keep doing it, keep doing it, and eventually we get to the value of 1. So in fact, what this equals is not 0 over 0, but it equals 1. And that's the limiting value. Now the reason for this, of course, is that it tells us that the limit as x goes to 0 of sine x is equal to x. This is something we'll use later, so remember this. Because we'll use this later. That's what it equals, and therefore, what this really is, this limit is, the limit as x goes to 0 of sine x is x. The denominator is just x. They cancel, and you get 1, which is this value right here. So that's how you can see how taking the limit, you have to be very careful in sneaking up on something from one side. Okay, so let me show you how you can use this to do something practical, like find the area of a circle. So suppose you have a circle with a radius r, and I want to know what the area of this circle is. How would you do that using the concept of a limit? Now you might say, I already know what the area of a circle is, but bear with me because this will show you how you can actually figure out what the area of a circle is without having to have somebody tell you what the answer is. So what we're going to do is we're going to approximate this with a square. And this square has approximately the area of this circle. It's a little bit bigger. The edge of a side here is 2r, and therefore the area of the square is 4r squared. So that's a pretty good estimate. Now you might say, well, I could have not used a square that's bigger than the circle. I could have used a square that's smaller than the circle, and I could have used this blue one, and I could use that as an estimate. Its area, if you work through the trig, which I'll let you do for yourself, the area is 2r squared of that. Okay. Now imagine we put this on a number line here, and what we can do is we now know that the area of a circle cannot be smaller than this, and it can't be bigger than this. Okay. So let's imagine we take the average, because we know that it's going to be somewhere in between, so the average might be a pretty good estimate. So it's less than 4r squared, bigger than 2r squared. If we average it, it's somewhere in there, and we're going to choose it to be right here in the middle, which is 3r squared. It's a decent estimate. So this is sort of calculus sort of thinking. Now, of course, what's the real answer? The real answer, the area of a circle, is pi r squared, which you already know from geometry. Well, that's not bad. Notice that we got 3r squared, and the real answer is 3.1r squared. So what we've done is we've bounded the answer and got very close to the real answer. But we haven't used the concept of a limit yet. But what we've been able to do is use knowledge that we do know, the area of a square, to our advantage to bound the real answer. Can we use more squares to get even more precise? So what I can do is take this same situation and just add rectangles, because I know the area of rectangles. Similarly, that will tell me that I'm not in this range. The green one tells me I'm not in this range. Now suppose I subtract some rectangles from the green area. That tells me I know the area of a circle is not in here. So I'm getting closer to bounding the answer. And what I want to do is be able to take that limit, and I want to just keep going. Now the problem with this procedure that I'm showing you here is that it's easy to understand. Even my mom, I was showing this to my mom, and she says, hey, why don't you put a triangle right there? And you can keep going. And that tells me that my mom knows how to think about calculus. But it's tedious to do this. And hundreds of years ago, thousands of years ago, when people were trying to figure this stuff out, like Archimedes and others, they tried to do this, and it was often very tedious. So what they did is they developed very systematic ways of taking this limit. So let's try to make this systematic using a polygon. And this is very close to what Archimedes actually did. Suppose we want to, instead of doing the area, we're going to do the circumference. So we want to know the circumference of this circle. And what we're going to do is approximate it with this polygon. Now this polygon right here is a very special polygon called a triangle. So this triangle has three sides. They have length L. They're all the same. And because this is a three-sided polygon, I'm going to write this as L3 to keep track of the fact that the length of the side of a triangle is not the same as the length of the side of another polygon. And what I notice is that the circumference is approximately 3, because there are three sides, times L3. Okay. Now what if I had a four-sided polygon? So let's call this L4. L4, the 4 just reminds me that it's the length of the side of a four-sided polygon, which of course is just a square. And the circumference here is approximately 4 times L4. So you see I've set up a pattern. The pattern is the circumference of a circle is approximately equal to the number of sides of a polygon times the length of a side of a polygon. And what I want to do is write that in mathematical notation using this concept of a limit. The limit as n goes to infinity of n, L, n. And that should give me the circumference of the circle. Now notice something that's very interesting here. This is a product of n times ln as n goes to infinity. This is becoming really, really large. But notice as I go from L3 to L4, the length of a side got a little bit shorter. So this is becoming really large, this is becoming really small, and the hope is that this gives a finite result, which is the circumference of a circle. So let's see how that can happen as the number of sides becomes larger and larger and larger. We get more sides to the polygons, and we approximate the circumference of the circle quite well, going up to here to 40. And here are some of the polygons that have to be used to be able to make this approximation. So let's get busy and try to figure that out. So what we need are some general rules. And these are the sort of things that we do in calculus because we want to make this systematic. So one of the things we notice is that the interior angle, this one, this interior angle is given by this expression. So this is the sort of thing where you use some algebra to come up with a very general rule. So for example, for a triangle, this interior angle will be 3 minus 2, 180 degrees divided by 3, because n is the number of sides here, and this gives us 60 degrees. And of course you knew this because an equilateral triangle, 60, 60, 60 degrees. If we had had a square, the next polygon, right? This is what a square looks like. Let's try that. That would be 4 minus 2 over 4 times 180, and that equals 90 degrees. And perfect agreement to what we see here. So this is a sort of way you can see a very general rule. Notice that as n goes to infinity of this interior angle, if I neglect this 2, I can cancel this, and this just gives me 180 degrees, which tells me that as I go to larger and larger polygons, this opens up to the point where it becomes basically 180 degrees, which is basically the tangent line at that point. Same thing here, I will produce a tangent line at this point and this point. But as I have more polygons, I will fill that in even more. So you can see that here. And you can see I start to approximate the circle by a large number of tangent lines. Okay, so let's get back to our calculation of the circumference of a circle. So what I need to do, if you remember, is I need to get the circumference of the circle, which I approximate as the limit. I don't approximate it, I compute it as n goes to infinity of ln. This part's easy. I need the length of the side of a polygon. So I write this triangle like this. I have some angle here, theta. This is the radius of a circle. This is the radius of a circle. And this is the length of the side of a polygon for radius r with opening angle theta. And this is what I need to stick in here. Now that might seem kind of abstract, so let me draw that for you in the context of a four-sided polygon or a square. So that's what I need. Turns out this is actually really easy to do. So let's just do it over here. If I take this triangle, go like this angle is theta over 2. Sine theta over 2 will be the opposite over the hypotenuse. So sine theta over 2 is L over 2 divided by R. So that's obvious where that comes from, just using the definition of the sine. Using a little algebra, I can solve this equation for L, and I'm almost there. All I need now is theta. And what is this angle? Well, we know from trigonometry that the total angle, if I go all the way around, is 2 pi. That's this. And if my polygon has n sides, this angle right here is going to be 2 pi divided by the number of sides. So if I have triangle, I have to go 2 pi to go all the way around, but this angle, and this angle, that's each of those is 1/3 of 2 pi. Just like here, I have 1, 2, 3, 4 angles to go around. So that's what the angle theta is in terms of the number of sides. So this is a matter of just plugging things in. The circumference now equals the limit as n goes to infinity of n times L, which is 2r sine theta, which is 2 pi, And the number of angles is equal to the number of sides, so I'll write that as a little n. And then there's a 2 right here, which is 2. I can cancel these 2's. Now I want to take this limit. And remember the limit that we took earlier when we showed that the limit of sine x was, when x became small, was equal to x. So let's use that here again. In that case, sine of the argument becomes just the argument, which is pi divided by n. Can cancel these n's. The limit's easy to take, and the circumference of the circle is 2 pi r for any r. And just using trigonometry and the concept of a limit, I have derived the circumference of a circle. Now we started off by talking about the area of a circle, so you're probably wondering about that. So let's do the area. The area is actually really easy now. Now that we've done this, it's really simple. We go, n goes to infinity, we need the area of this circle. Sorry, the area of this triangle is going to be n of n triangles, and the area of one triangle is 1/2 the base times the height. Now using trigonometry again, we're going to use the cosine. We need the adjacent. So that's going to be r cosine theta over 2. Using the fact that the cosine is the adjacent over the hypotenuse, and the hypotenuse is equal to the radius. So I get this relationship. Now let me put up this curve, these curves up here. Notice that the limit as the argument of cosine goes to 0 goes to 1. And I want to use that relationship because theta over here, as n goes to infinity, theta becomes really small. So what I'm going to do is I'm going to simply neglect this term here because it goes to 1. Okay, then I'm going to have n L over 2. Still need my limit here, equals this. And I need to substitute what L is from over here, which is 2r. And then I already know what the limit of this is. It's going to be just the argument, which is 2 pi over n times 2. And then I have an n that cancels an n, a 2 that cancels a 2, another 2 that cancels a 2, and I'm left with pi r squared. And now again, using trigonometry and taking a limit, I have derived the area of a circle for any circle with radius r. And this is what calculus is really about, is using limits to describe objects that have curves or they're changing. And that is the basic idea of calculus. Okay, so in summary, calculus is about limits. We've seen that with the sequence. We've seen that with the function sine x over x. We've used the concept of a limit to derive things that previously you probably have only been told, like the circumference and area of a circle. And fundamentally, this allows us to see how things change. And that's what calculus is all about. That's what distinguishes it from other areas of math. Okay, so now when you study calculus, I just want to let you know that it's usually divided up into 2 branches. The way I've described it so far, it's about change, it's about limits. It's all one thing, but typically people like to break it up into curves and slopes and areas, or when you get to a little bit more advanced, you might actually do things in 2D and 3D and do volumes and things like that. So, of course, in math, you have to have fancy names for things. So slopes are usually referred to as derivatives, but nothing fancy. Just remember that word. It's nothing complicated. And areas and volumes are called integrals. And so you'll see these words, derivatives and integrals. There's nothing fancy about them. You already understand what they are if you've watched this video up to this point. And so the 2 branches of calculus then derive their names from these words. One is called differential calculus, that side, and the other one is called integral calculus. And so nothing fancy about those names, but you'll often see those names used in textbooks or other places. And just keep in mind that it's very simple. Differential calculus uses the concept of a tangent line to figure out what the slope is for a changing curve, whereas integral calculus tries to figure out how to get the area under a curve or between two curves or whatever, and that's called an integral. And of course, differential calculus could be used to figure out how fast this roller coaster is going, and integral calculus might be used to tell us how much green fabric do we need to cover around this balloon, or some other problem. You can sort of see the idea. Everywhere you go around you, you'll see calculus everywhere in pretty much everything that you see or experience. Okay, now if you just picked up a calculus book, it probably would look to you to be very complicated. And the reason is they like to use very precise notation, which is good. But let me just tell you what that notation is and how it's used. So this symbol right here is used to represent a derivative, and this symbol is used to represent an integral. So nothing fancy. This is the way you say this is the derivative with respect to x of x to the n is n x to the n minus 1. Now, see, where did this come from? This is one of the things that's derived in calculus using the concept of a limit. And I'm not going to go into it because the derivation, that's not that interesting and useful. And in fact, when you do calculus, you often just go look these things up. If you have a calculus textbook, these table of derivatives is usually in the back of the book, or you can look it up on the internet or anywhere else. Same thing for the integrals. These things are tabulated everywhere. Once you learn these and memorize a few and understand them, once you're using them, whether it's in finance or biology, physics, mechanical engineering, aerospace engineering, by the time you get to that, you're just looking these things up in tables. And in practice, that's how you actually do it. Now, but it is interesting to look at the tables and think about, from a calculus point of view, what they're telling you. So let's look at this one really quickly just to show you something very interesting. And that is that the derivative of sine of x equals cosine of x. What does that mean? It means, remember that this means find the slope of this function. And the slopes of this function is a function. Remember when we had a line, there's only one slope. Now, the slope of this function is itself another function. So let's go over here, and I plotted some of these up. Let's look at the slopes of sine, and the slopes of sine are given by cosine. What does that mean? What it means is if we look at this curve, it tells us the slopes, or the derivative of that curve. Let's see if that works. So when cosine x is 1, the slope of sine x is 1. When cosine x is 0, the slope of sine x is 0. When cosine x is minus 1, the slope of sine x is minus 1. And then it keeps on going. 0, 0, 1, 0, and of course everything else in between. And that's what this is basically telling you. It's pretty interesting. And what's interesting, you could keep going, is that the cosine x, the derivative of that, is sine x. So I can keep on going, and you can do this as a practice problem to show how this gives the slopes of that curve. And in fact, there's a notation that I should show you that's the second derivative. It's nothing fancy. It just says do it twice. The second derivative of sine x, since I go here, is equal to minus sine x. Because the first derivative is cosine, and then if I take the derivative of that, I get sine. So the second derivative of x is minus sine x. And you can keep on going just like that. Same thing is true for the integrals. You can look them up. Notice the one thing about integrals that's very interesting and why these are paired the way they are is if I take the integral of cosine, it gives me a sine, just like the derivative of sine gave me the cosine. Basically, integrals are the inverses of derivatives. And that's why you usually learn about these first, and then later you learn about these. So that's just a little bit of insider notation so you don't get confused. So let's review again what calculus is. I just want you to not go away without being able to say out loud what calculus is. Algebra is the study of operations like multiplication and division and so forth, and equations like we've seen. Trigonometry is a study of triangles. We've used both of these so far. Geometry is the mathematics of shape. That's what it does that's different from algebra. And what calculus does is it uses a concept of limit to look at things that are changing. And if you keep that in mind while you learn calculus, it makes it a lot more interesting, and it makes it a lot clearer what it is that you're trying to do. So what can we do with this, and does anybody really care about calculus? So let me just give you 3 quick examples of how you might use it. One way you might use it if you're learning engineering or science or whatever is to use it to graph a function. And this is a very useful thing. Suppose I have this function f of x, and it's this green curve right here. What I can do is I can use 2 concepts from calculus very quickly to help me plot this. Suppose I do something like take the limit as x goes to infinity of f of x. And if you look at this function, just this concept will tell you that if x becomes really large and negative, this isn't going to matter. But if this, because this is x squared, eventually this is going to be much larger than this. And so roughly this is going to go like x squared. Notice that the same is true if I had put minus infinity here. Nothing would have changed. So this tells us that this function goes up very quickly out here and out here. But we don't really know. It doesn't tell us what's going on sort of in this intermediate region. That's where we can use the actual concept of a derivative, the derivative of f with respect to x, which often uses this notation f prime. I just wanted to throw that in there in case you see that sometimes. Anyway, this is just a notation for the derivative. If I use those tables that I showed in a previous graph, I find that the derivative of this function is 2x minus 1. So that is, the derivative is this curve. And what does it say? It says that it's positive. Notice that this curve over here is positive and it's increasing. So the slopes are positive and getting bigger and bigger and bigger and bigger. If I'm over here, the slopes are negative and getting more negative. Negative, 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 negative. That's what it would do. But I can also set the derivative to be equal to 0. And I can solve that equation. When the derivative is 0, x is 1/2. So if I look right here at x equals 1/2, I go up, sure enough, the derivative is 0. So this tells me something about this function. It says that right in here, there is a 0 derivative, and because it goes up to the right and up to the left, I have located the minimum of the function using calculus. Now, why would you care about finding the minimum of a function or the maximum of a function? Because calculus, you can see, does it very quickly and easy for you. Once you know what the derivative is, you know what the slopes are. You know if the slope is 0, you're either at a maximum, or potentially you could be also at a maximum or a minimum. Okay, so you can use this to make the world a better place using the concept of optimization. Make the world better through engineering, decision making, economics, finance, agriculture, airline traffic, whatever it is. And basically the way calculus does this is, imagine you have a function and it's a function of several variables. Here I'll just do it in terms of 2 because that's all I can put on the screen, x and y. Calculus allows me to find this value very straightforwardly. And that might mean an engine that has the best gas mileage, or it might mean a retirement plan for which I can retire at the earliest possible date, or whatever it is. Calculus can be used to make the world a much better place by allowing us to mathematically formulate a problem and then find the optimal solution that we're seeking. Okay, so one last example where calculus is used is anywhere and everywhere in engineering and science. And now I'm going to introduce the concept of a differential equation. Now this is something that you often learn at the end of calculus, possibly, or even in a class after calculus. But I wanted to introduce it here because it's so important, and historically it motivates the reason of why calculus actually exists. So let's go through and see how that comes about. So suppose you're in your car and you want to go somewhere and your position is x. Maybe you're going to the store. So your position starts off with you being at home, and over time, t, you end up at the store. So what you do is you get in your car and you need to go up to some velocity, and the velocity is nothing more than the change in the distance that you're going over some period of time. For example, miles per hour is your velocity, or could be meters per second or something. That's your velocity. That's just a derivative. So next time you drive your car, think about calculus. Now, if you're starting from rest, your car's sitting there in the driveway, you need to accelerate to get your car up to some velocity over some period of time. So the acceleration is also given by a derivative. So next time you're in a car or a bus or an airplane and you accelerate, think about calculus. That's what you're doing, is it's telling you how your velocity is changing, and as your velocity changes, your position can change. Now, let's look at this equation, F equals ma. This is an equation from physics and used everywhere in science and engineering. And it says that the force on an object is equal to the mass of the object times the acceleration of the object. The acceleration, we know, is just given right here. Now, let's look at a specific equation like this one, where the force depends on the position. So imagine we have our roller coaster, and wherever it is, there's the force of gravity, and of course the force of gravity is going to depend on where the roller coaster is. So that's why we write it as f of x. And we write the mass, and then we just substitute in from these expressions that the acceleration is the second derivative by using these relationships. We get this expression for the acceleration, and we can describe something like a roller coaster going down, and maybe our goal is to figure out like how fast is it going at the bottom so we can make sure that this is safe. That would be a great application of calculus. Now, instead of doing that, let's consider something that's really easy to visualize. Imagine instead of having this situation for the force, imagine we have a force that has this functional form, minus k just times x. So what it would mean is if the particle, if I take this little object, particle, whatever it is, and I move it over here, the force is negative and it tries to push it back. Similarly, if I try to push it this way, x is minus, the force would try to push it back to 0. X equals 0. Okay, that's what this force does. It's a simple force, but I wrote it this simple way because it shows that I have an equation. So I have an equation. It is an equation for x as a function of time, and it involves a second derivative, and therefore this thing is a differential equation. It's a differential equation, and because it's an equation that involves derivatives. Now, of course, what this is nothing more than the equation for an object connected to a spring. If I pull it too far, it goes back, and if I push it too hard, it also tries to spring back. And so this is an example of where this equation right here describes this motion. And of course, all of this was discovered and developed early on by Sir Isaac Newton, who actually was trying to understand things like Newton's laws. And this is one of Newton's laws, or trying to understand gravity, and developed calculus because he realized all of the other types of math that were available to him couldn't solve this problem. And therefore, he set out to solve that problem and had to invent calculus to do it. Okay, so we're done, but let's review where we are. Keep in mind that the new thing is here is calculus looks at things that are changing, like that spring going back and forth and back and forth. It's constantly changing, and it requires the concept of a limit, which led to, for example, the concept of a derivative or an integral, and led to, for example, a differential equation that describes the spring. Calculus is used literally everywhere. Now that you know a little bit about calculus, you're going to see it happening all around you, because everything is a curve, everything is something moving and changing, but it's also used every day to make the world a better place through optimization, engineering better products, understanding new things in physics and so forth. It is absolutely everywhere, and it's crucial. Now, the one thing that we've seen is the basic idea in calculus is approximating something you know in terms of something you don't know in terms of something you do know. So we often, when we derive some of the expressions, we use things like, what do we know about rectangles? What do we know about triangles? What do we know about polygons? And we used all those things that we do know from other types of math, and then we finally found a limit. So you got to bring in everything you know about geometry and algebra and take a limit, and then you can get results in calculus. Finally, calculus is divided up into differential calculus, which looks at slopes, and integral calculus, which looks at things like areas and volumes. And when you study calculus, you'll usually do this first, and then you'll do this second, typically, and that's usually how it works. Okay, so here's a quiz. I recommend you pausing the video, reading these questions, going back, finding the answers, whatever it takes. Make sure that you can say these answers out loud, and if you do, you fundamentally understand what calculus is, and learning calculus should become a breeze at that point. Okay, with that, I hope to see you here at New Planet School for another video. Thank you.